And then next up is Emerson Whittaker, going to talk to us about libration. If, like Emerson did, the speaker for the next session can come up once the questions start. I appreciate it because I'm going to forget to mention that every time.
All right. Hi, everyone. Can you all hear me okay? All right. Hi, my name is Emerson Whittaker. I'm a fifth-year grad student at UCLA working with Jean-Luc Margot. And today I'm just going over work that I'm sort of still in the middle on, trying to get a shape model of the secondary in the 1999 KW4 system that can account for its libration, and then hopefully be able to extract out how fast the secondary is moving away from the primary. Okay, so just a little bit of background. So about 16% of near-Earth asteroids are thought to be actually binary systems rather than single asteroids, and that's just coming from radar data, but there's other estimates that are about the same from other sources. And how these systems form and evolve affects when and how they're going to pose an impact threat to Earth. And so using a case study of the binary asteroid system 1999 KW4, we wish to address two different questions. One being, what's the average lifetime of a near-Earth asteroid binary system? And two being, which effects dominate this lifetime through the mutual orbital evolution? So why do we pick this system in particular? Well, there's a number of reasons. Basically, this system is very well characterized, and it was important for pioneering our current understanding of these asteroid binaries. So they have, there's exceptionally high resolution radar data taken of the system in 2001, and some pretty great radar data from 2002 as well. And it's the third binary system ever imaged by radar, and the first one imaged in detail. And so using this 2001 and 2002 data, Ostro et al. 2006 was able to get a pretty good shape model of the primary and secondary that taught us a lot about these near-Earth asteroid binaries. First of all, that the primary had a distinctly top-like shape, which we now know to be characteristic of these bodies. And they were able to measure the masses and the densities of both components via their reflex motion and the shape of the secondary, which allowed for a detailed study of the dynamics in Shears et al. And so pairing both of those studies together, they saw a top shape for the primary, that the primary was rotating rapidly, that it had a low density, and coupled with the simulations that provided some of the first evidence for asteroidal fission forming this binary system. So the idea being you had some sort of rubble pile primary that spun itself up fast enough that it split into two pieces. And this could be due to either the Yorp effect or tidal evolution effects. So a little bit more about this system specifically. The primary is 66391 Mashup. It's about 1.5 kilometers across. The secondary is called Squanit. It's about half a kilometer in diameter. And the secondary, at least from the 2006 study, seemed to have a significantly larger or higher density than the primary, which is atypical and could be indicating a problem with the shape model. And then they have a 17-hour mutual orbit, and this orbit can be subject to change by a number of different forces. So there's tidal interactions between the bodies. There's the binary Yorp effect, which is sort of one of the main effects where the sunlight is being absorbed by the body and then being re-radiated in such a way that it adds angular momentum to the system, or it can actually work against the angular momentum of the system. And then there's some other re-radiation effects that I won't address as directly with this study, but things to think about like binary Yarkovsky and other effects. So this system was imaged by radar from the Arecibo Observatory and the Goldstone Observatory in 2001 and 2002, but also again in 2017, 18, and 19. And so that data will be coming in later, as you'll see. But here you can see the stacked images from Arecibo there on the left and from Goldstone on the right. And so the thing about radar images is they're not really the same as normal images. The up and down direction is actually sort of the direction along the line of sight of the observer, and then left to right is actually the Doppler shifted velocity. So a little bit difficult to look at, but the oval shaped thing is the primary, and then the little streaking thing is the secondary there. Okay, so just to give a little bit of an overview of the physics, if we're considering the tidal evolution and the binary Yorp effect, if we assume those are going to be the main sources of what's evolving the orbit, in this case, the primary is rotating faster than the secondary, and the secondary is in tidally locked, so its orbital period is the same as its rotation period. And so in that case, tidal evolution is always going to be acting to expand the system, whereas the Bjork effect could be acting in either direction. And that's going to be depending on things like small scale topography and things that are difficult to measure directly. So if you imagine a toy model where it's triangle shaped, if you suspend your disbelief, in this case, the sunlight would be being re-radiated more in the negative direction on this side of the orbit than on the opposite side. And so that's going to add a net torque, which is working in the same direction as the tidal evolution. Whereas if it were the opposite shape, then it would have a torque in the opposite direction that's acting against the tidal evolution. And so this means you could have the orbit evolving inwards or outwards, although the outwards direction is sort of favored depending on how strong the tidal evolution is. So in terms of what we've actually measured, it looks like the system is expanding, but overall how much it's expanding is still contested. So based on a study by McMahon in 2010, they used the radar shape model from the Ostro study, and they found an expansion of 7 centimeters per year. But this made a couple of different assumptions. And then a different study by Shirich et al. That actually didn't use the radar data, but was using light curves and fitting to light curves, assuming first a spherical, then an ellipsoidal shape, found an expansion rate of 1.2 centimeters per year. But obviously this involved a whole host of assumptions. So the jury's still out on what the actual expansion rate is for this system. And then to get to previous shape modeling, this is the primary on the top, the secondary on the bottom. And so with this model, the residuals combined with the dynamical simulations suggest that Squannet may have a noticeable libration in longitude, but the previous shape model that was used wasn't able to account for such a libration. But improvements that have since happened with Nadu et al. In 2015 can now allow the code to include a longitudinal libration. So that's what we're planning to add. So our goal is to refine the center of mass measurements by fitting for a new shape model with libration and using these centers of mass to measure the mutual orbital expansion rate. And so part one will be creating an improved shape model for Squannet that accounts for its longitudinal libration. And then part two is combining the center of mass locations that have been improved by that shape model to these radar observations spanning all the way through 2019, and then using that to measure the mutual orbital expansion rate by directly fitting for it. And this is what we have so far. So we're sort of halfway into part one. And so this reduced chi-squared here is showing librational amplitude versus the libration phase. And so the best fitting amplitude is at 4 degrees for the libration, with the libration phase being at 230 degrees. And however, the fit isn't necessarily statistically significant, as you can see sort of the differences in the chi-squared values are very low. So this remains ongoing to try and figure out whether or not this libration is going to be actually significant. And then you can actually see the shape model here on the right. So so far we found that the libration amplitude around 4 degrees seems to be favored, but the model refinement is still ongoing. And once we determine the optimal shape model, we'll use it in combination with the more recent radar data to measure the mutual orbital expansion rate. Thank you, and I'll take some questions now.
Thanks. Definitely have time for a question or two.
Hi, it's a very interesting object. I'm actually wondering if there are any dynamical or theory constraints on what the libration amplitude ought to be.
So that is a good question. Anecdotally, I don't think anyone expects the libration to be extremely large, just because based on one of the NADU papers, I think it's a different NADU 2015 paper, but if we assume that it's not excited, the librational excited amplitude would have to be where all of this is coming from, because if we assume that it's not an excited amplitude, then it should be really close to zero because the eccentricity is so low for the system. But then again, that's using ellipsoidal models versus the radar shape models. So when you account for the fact that the shapes are actually more complicated, that adds another layer of complexity. So I think basically people expect it to be probably under like, 10 or 20 degrees, but no one knows for sure, I don't think.
Great. Any other questions? I think actually on time-wise, we're doing just right. So thanks. Let's thank our speaker again. Thank you very much.